Welcome to the session on sequences and series, geometric series, sum to infinity. The objectives for this session are to prove the formula for the sum to infinity of a convergent geometric series and apply it. Before we begin, let's review geometric sequences. The formula for the nth term of a geometric sequence is u subscript n equals a times r to the power n minus 1, where u subscript n is the nth term, a is the first term, and r is the common ratio. Let's take a look at an example. An increasing geometric sequence could be of the form 3, 12, 48, and 192, and so on. We've multiplied each term in the sequence by the same number, namely 4, to obtain the next term in the sequence. So 3 has been multiplied by 4 to give 12. 12 has also been multiplied by 4 to give 48. And 48 has also been multiplied by 4 to give 192. Let's also review geometric series. A geometric series is the sum of the terms of a geometric sequence. The sum of a geometric series is s subscript n equals a times 1 minus r to the power n all over 1 minus r, where r does not equal 1. Again, let's take a look at an example. A geometric series is when all of these numbers are added up. So the terms of the geometric sequence in example 1 are added together to give 3 plus 12 plus 48 plus 192. S subscript n denotes the sum of the first n terms of a series. So in this example, S subscript 4 is equal to 3 plus 12 plus 48 plus 192, which is 255. We're now going to take a look at the sum to infinity. So what happens when n goes towards infinity? We've already established that the sum of the first n terms of a geometric series is s subscript n equals a times 1 minus r to the power n all over 1 minus r, where of course r does not equal 1. As n tends to infinity, and this is written as n arrow infinity, the sum of the series s infinity is called the sum to infinity. Let's take a look at an example. Consider the first n terms of a geometric series, which looks like this. So 3 plus 9 plus 27 plus 81 plus, and so on. Since the terms of this series are getting larger, as n tends to infinity, we have that s subscript n also tends to infinity. And this is called a divergent series. Now let's consider another example. Consider the first n terms of the geometric series, a third plus a ninth plus a 27th plus 1 over 81 plus, and so on. Since the terms of this series are getting smaller, we have that as n tends to infinity, s subscript n tends to a finite value, s subscript infinity. This is called a convergent series. A geometric series is convergent if and only if mod r is less than 1. This can be written as minus 1 is less than r is less than 1. Now when mod r is less than 1, we have that the limit as n is going towards infinity, or n is tending to infinity, of a times 1 minus r to the power n all over 1 minus r, in other words the sum of the geometric series, is equal to a over 1 minus r. And this is because r to the power n, which is less than 1, is tending to 0 as n tends to infinity. So in the numerator, we have that the limit of that is going towards a. And of course here, limit n tending to infinity is this symbol here. So for a convergent geometric series, the sum to infinity is s subscript infinity equals a over 1 minus r. Let's now apply this to an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. Consider a geometric series whose fourth term is 0.686 and whose sixth term is 0.33614. You are required to show that the series is convergent. So let's solve this. Since the nth term of a geometric series is a times r to the power n minus 1, we have ar cubed equals 0.686, since the fourth term is 0.686. We're going to call this equation 1. We also have that ar to the power 5 equals 0.33614, and this is because the sixth term is 0.33614, and we're going to call this equation 2. Let's now divide equation 2 by equation 1, and we're doing this to allow the a's to cancel so that we only have r left in our new equation. So here's equation 2 in the numerator, and here's equation 1 in the denominator. So we have ar to the power 5 over ar cubed equals 0.33614 over 0.686. And this is equal to 0.49. In other words, r squared is equal to 0.49. And this, of course, implies that r is equal to 0.7. Now, since mod r is equal to 0.7, and this is less than 1, we have that the series is convergent. Now let's take a look at part B. We are required to write down the sum to infinity of the series. So let's solve this. From part A, we have that r is equal to 0.7. We also have equation 1, which states that ar cubed equals 0.686. So now we can simply plug in r equals 0.7 into our equation in order to find a. So substituting r equals 0.7 into equation 1, as shown here, gives us a times 0.7 cubed equals 0.686. And if we rearrange this, we can solve for a. To give a equals 2. And now we can substitute a and r into the formula for s subscript infinity, as shown here. So we have a equals 2 over 1 minus r, which is 1 minus 0.7. So here's a equals 2, and here's r equals 0.7. Which is equal to 6 2/3. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at this. We have that a geometric series has first term a and common ratio r. It also has that the sum of the first 4 terms, S4, is equal to 9.375 and S infinity equals 10. Given that all the terms in the series are positive, find the values of a and r. So let's solve this. Now S subscript 4 equals a times 1 minus r to the power 4 all over 1 minus r. We've substituted n equals 4 into the formula for Sn. And this is of course equal to 9.375. We're going to call this equation 1. We also have that S subscript infinity equals a over 1 minus r. And in our example, this is equal to 10. So a over 1 minus r equals 10. And we're going to call this equation 2. Looking closely at both equations, we can see that a over 1 minus r appears in both. And so we can substitute 10 in place of a over 1 minus r in equation 1, as shown here. So we have in our new equation 10 times 1 minus r to the power 4 equals 9.375. We now have one equation and one unknown in it. So rearranging this gives us that r to the power 4 equals 0.0625. And hence r equals the fourth root of 0.0625, which is equal to plus or minus 0.5. If we substitute r equals 0.5 in equation 2, we have a over 1 minus 0.5 equals 10. Giving us that a equals 2. And if we substitute r equals minus 0.5 in equation 2, we have that a equals 15. Now, since r is negative and a is positive, in this part, we can now conclude that r cannot be negative, since as part of the question we know that all the terms in the series are positive. Therefore, r equals minus 0.5 is not possible. And therefore a equals 2 and r equals 0.5. This brings us to the end of this session. If you have understood its contents, you should be able to prove the formula for the sum to infinity of a convergent geometric series and apply it. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.